So good afternoon everyone. Please ask your friends to join quickly. If anybody is there still, I think around 50 plus join. So message to the remaining your friends also to join quickly. Sorry for the delay. There is a small topic that we are going to discuss today, and it is also today's last class. So there is no problem with time. Okay, there is no the topic will be so. So we have successfully completed the first chapter. First chapter is over. So I will give you the highlights of the first chapter. In first chapter, we have seen the introduction to the state space, and we have clearly identified the difference between the transfer function analysis and state space analysis. We have seen the advantages of state space analysis. We have also came to know that in state space, the representation of the system in state space itself is a task. Okay, we have realized that. So for representing a given system in state space itself, we have almost concentrated in single chapter, that is first chapter. Okay. We should always keep it in mind. Okay. The analysis part is the second part only for representing itself. It is complete first chapter. After representing, so what are the various formats of representations? Okay. Uh, we know that the state space representation is not unique. There are many representations possible, unlike transfer function analysis, where in transfer function analysis it is single or unique representation, whereas the state space representation is not unique. You can get infinite number of representations depending upon the choice of the state variables. Choice of state variables. Okay. So after representing, we have seen the solution. The solution of state space equations. Okay. State equation, output equation. Two set of equations will be there. Out of those two set of equations, we have to solve for the state equation, and then we have to substitute it in the output equation so that we will clearly get an idea about the output or the response of the system, so that we can comment on stability of the system. We can comment whether the system is following the response is following input exactly or not. If there are any errors, it allows us to design a suitable controller comfortably. So it is better to have a good idea about the mathematical equation of the output that can be obtained through the solution of the state space equation. There we got an important topic or important element. We can say it is called state transition matrix. Remember it. It is very important. I am so the state transition matrix is very important. I think I have given you the tasks regarding the state transition matrix. One thing is you should identify what is the significance of the state transition matrix. Second one is you have to identify the properties of the state transition matrix. Okay. There will be a compulsory question on state transition matrix, whether it may be on properties or whether it may be on the significance, or whether it may be a numerical example given to you in which a system is represented in state space, and you need to find out the state transition matrix. And you should always remember that Si minus A whole inverse, that matrix is having high importance as long as we solve for, as long as we deal with the solution, or as long as we deal with the state transition matrix. Okay. I hope all of you have gone through those exercises or those tasks that are given to you. Okay. So it is your duty to go through those topics and don't postpone or don't keep them pending. Okay. Complete it as soon as I end the class, okay, so that there will be a proper continuation towards the next topic. So let us move to the second chapter. Second chapter, as I told you already, in the second chapter, what we are going to, we have spent enough time on what knowing what is state space analysis, what is state space representation, how to convert transfer function to state space and state space to transfer function. And I have also given you the clear idea how to convert a transfer function to state space via signal program. So we have spent enough time. We have completely learned representation part. Okay, the second chapter, it is all the analysis part. Okay. Now, with the knowledge of what we have learned in first chapter, we are going to analysis the real-time systems, not the systems given. Okay. So that is about the second chapter. In the second chapter, let us first concentrate on the two important aspects of the system, that is controllability and observability. Controllability and observability. Okay. These two are very important, very easy. Here you need to identify whether the given system is completely controllable or not, whether the given system is completely observable or not. So I will give you the meaning of controllability and observability in a moment. But the idea is you have to say whether the given system is controllable or not, whether the given system is observable or not. Okay. Small topic, easy topic, but important topic. Almost all the 50% of the questions, whether it may be university exam or whether it may be competitive exams like GATE, you will get from today's class. That is controllability and observability. Some system is given to you and you need to find out whether that system is controllable or not. Similarly, some other system is given to you. You need to find out whether the system is observable. Okay. Very important topic. I am saying it again. 50% of the questions from this chapter. Okay. In university exam, there will be a compulsory chapter on controllability and observability. So let us see here. So we know that any system can be represented in state space with the help of the state variables. So what are the state variables? These are the minimum number of variables that are enough to describe all the dynamics of the system or all the parameters of the system. Okay. See here in the diagram I have given to you. The bigger circle is all the variables that are available in the system. So if you recollect that the very first example we have solved, that is in that example I have taken a simple RLC circuit and I have solved or I have obtained its state space representation. Where what are the system variables available there? Inductor current, capacitor current, inductor voltage, capacitor voltage, resistor current and resistor voltage. Total 6 variables are available. 6 variables. Out of those 6 variables, how many variables we have considered as state variable? Only 2 state variables. Why? Why only 2? We know. The number of state variables to be selected is based on the order of the system. That is a second order system. So 2 variables are enough to represent it in the state space. Now, here in the concept of coming to the concept of controllability and observability, we are going to concentrate on those 2 state variables only. On those 2 state variables are for a nth order system, n state variables. Those n state variables from the input side as well as output side, or from the input end or as well as output end. We are going to manage. We are going to how we are going to manage them. Why we are going to manage them, I will tell you later. As of now, from input side or output side, we need to carefully manage these state variables, especially in the design process. In the design process, if we can able to manage them, or if we can able to alter them successfully according to the user's requirement, or according to our requirement, then we can design a suitable controller that much easily and that much perfectly. Okay, if you can manage all the state variables, then we can design excellent controller. If you cannot manage all the state variables, or if you cannot deal with all the state variables, you won't get a perfect controller while designing. That is the idea. Okay, coming to the managing, or coming to the altering, or whatever it may be, dealing with the state variables, we have 2 options. One is from input side, second one is from output side. From input end and output end, we can manage these state variables. Okay. Controllability is the concept. Controllability is the concept that is related to when we manage the state variables from input side. When we manage the state variables from input side. Similarly, observability is the concept. Observability is the concept we came across when we try to manage the state variables from output end. You should remember from now on. Like simply saying, whenever you are dealing with controllability means you are doing something on the system, that is you are doing something on the state variables from the input side. From the input side. Whenever you are dealing with observability, you are making changes on the state variables from the output side. From the output end. Why? Because these two are the only possibilities to access the state variable. Either we can access from input end or we can access from output end. Okay. If we are accessing from input end, we are it means we are dealing with controllability. If we are accessing from output end, it is observability. So if this is understood to you, the remaining task is nothing. It is nothing but simple mathematics. So controllability. Now you see the definition. To take a minute and read the definition. The input to a system can be found that takes every state variable from desired initial state to desired final state. The system is said to be completely controllable. Otherwise, the system is said to be uncontrollable. The system is said to be uncontrollable. Now I think you got the definition of controllability. I told you in the previous slide this clearly. Controllability from input and observability from output. Now This controllability can be obtained. We can comment on controllability by inspection or by some method, by some, not by applying some. It is like commenting on stability in case of transfer. So, but suppose if in case of transfer function, s square minus 2s plus something is there, then what is your comment on stability? You can directly say that system is unstable. Why? We know that the necessary condition according to Raut-Hurwitz criteria is all the coefficients of the characteristic equation must have same sign, either positive or negative. But here this is negative, this is positive, so it is having different sign. We can simply say that system is unstable. There is nothing to do. It is called commenting on something without any calculation, without any method. Okay, this is called commenting on by inspection. Similarly, we can comment on controllability also. If some system is given to you, you can say immediately it is controllable, but there is a condition. I will tell you what is that. Okay. Controllability by inspection and controllability. See here, there is a some system represented in parallel form using signal flow graph. There is a system represented in parallel form using signal flow graph. There is one more system represented using signal flow graph in parallel form. If you see this, first point I want to tell you is that if the equations are decoupled or the system is represented in parallel form, then only we can comment on controllability by inspection. Otherwise, we cannot comment on controllability by inspection. We have to apply a separate method. Now here if you see, this is the state variable 1, state variable 2, state variable 3. This is the derivative of state variable. You see, input is, all the state variables are connected through the input. All the state variables are connected through the input. It means by introducing some parameter at the input or by making some modifications in the input, I can influence every state variable. So this system is said to be controllable. Same here, if you see this, second variable is directly linked to the input. Third variable is, but there is no connection between first variable and it means the first variable I cannot control, first state variable I cannot control with the help of the input, or I can say that by making any changes at the input, I cannot reflect those changes for the state variable 1. Why? Because it is not depending on input. So this system is said to be not controllable. This system is said to be not controllable. Okay. Again, we can comment like this by simply inspection only when the system is represented in parallel form or state equations are decoupled. State equations are see those two signal flow graphs here they are represented in the state space analysis. Okay. Only diagonal elements, diagonal matrix equations are decoupled. Every state variable is linked to input. System is controlled. See, only diagonal elements. After remaining elements are zeros, but only second and third state variables are linked. There is no connection between first state variable and input, so it is zero. So this system is not controllable. Not controllable. See here, there is one more example. There is one more example. This is the first state variable and its derivative. Second state variable and its derivative. Third state variable and its derivative. If you see the signal flow graph, first and third are connected to input, but there is no connection between second state variable and input. Second state variable and input. And this is also parallel form. This signal flow graph is also parallel form, but there is a repeated route. Repeated route, that is why we got these cascade connection. This one, this one, both are in cascade. That cascade connection is because of repeated. So immediately, according to the previous knowledge, we can say that system is not controllable. Why? There is no connection between these. We can say that the system is not controllable, but it is wrong. So why? I will tell you. See here, the same system represented using signal flow graph. It is not pure diagonal matrix. It is not pure diagonal. There is an element. It means the equations are not decoupled. Equations are not decoupled. And this is the example of this is also a parallel form, but it is an example of Jordan representation. This particular block is called Jordan block. I asked you to refer. Might have it. This particular block is called Jordan block. The conclusion is, even though the signal is represented in parallel form, even though the signal is represented in parallel form, even though the system seems to be not controllable, we cannot proceed like this. Why? Here it is having a repeated root. -1 is the repeated. So you should add one more condition here, that controllability by inspection is applicable only when the equations are decoupled. That is, the system is represented in parallel form. And you should add one more condition now, is that it should not have any repeated roots. Should not have any repeated roots or repeated poles. not apply controllability through inspection. So that is about controllability through inspection. So now controllability using controllability matrix. These things you might have studied already. Okay? It is very easy, you know. So you should form a controllability matrix. This is the controllability matrix out of available matrices. That is, ABC matrices will be available for you in the state space. Using those three matrices, you should form a controllability matrix. So I told you already, controllability is with respect to input side. So we will take the help of input matrix and system matrix, and we will form this particular matrix. B, A, B, A square, B, and so on. Okay. So the idea is, after forming that matrix, if the rank of this matrix is n, then system is said to be controllable. If the rank of this matrix is n, then the system is given system is controllable. Controllable. You know how to find out the rank of the matrix. You refer the matrices once. You find out how to find. So it is nothing but the number of non-zero rows that are available after you represent your system or your matrix. After you are making some changes in row column transformation. Row column, you know the task. So you have to find out. So this is the one more way to find out, or this is the best way to find out the controllability matrix. Why? Because all the times you cannot find through the inspection. See, I am taking the same problem again. According to inspection, this is not controllable. But let us see according to method, that is matrix method, controllability matrix. Here controllability matrix obtained for this particular problem. What is the rank of this matrix? That is number of non-zero rows. Number of non-zero rows are 1, 2, 3. Number of non-zero rows are so this is a non-zero row. When you can say a row is a row as 0 row, so all the elements are zeros, then only you can say it is. Here all the elements are non-zero, so the rank of the matrix is 3. The system is completely controllable, But if you see the equation here, for the first state variable and input, you are getting 0 here. It seems like it is not controllable. But it is actually controllable through the method. And of course, if there are no non-zero rays, the determinant is also non-zero. The determinant is also non-zero. Okay. Suppose if this row is 0, if this row is 0, then you will get the determinant as 0. So you can say like that also. Okay. If the determinant of the controllability matrix is 0, then the system is not controllable. If the determinant of the controllability matrix is not 0, then the system is not controllable. Okay. You can follow any method. You can follow through the rank of the matrix, or you can follow through the determinant of the matrix. So it is your choice. So all the things that I have discussed with the controllability concept, controllability, are applicable through the for the observability also. Now you take a minute and read what is observability means. Okay. Observable is the reverse process. You can say it's the reverse process. we can able to successfully find out the initial uh, state vector, then the system is said to be observable. We cannot find out initial state vector from the response point of view, and the system is not observable or unobservable. Same. Okay. This is the first system. This is the second system. All the state represented in parallel form. That should equations are decoupled. There are no repeated loops. All the conditions must be, you must remember, it must be represented in parallel form. That is, equations are decoupled. There should not be any repeated poles or repeated eigenvalues. Then only we can comment on controllability through inspection. So all the state variables are connected through the output. The system is observable. Only two variables are connected. This is not connected. System is unobservable or not observable. Unobservable. Same explanation holds good for this also. Whatever we have explained for controllability holds good. See here. There you observe input matrix, here you observe output matrix, that is matrix C. Okay. All the elements are one means first state variable is connected, second state variable is connected, third state variable is connected. The system is observable. Second is connected, third is connected, first is not connected. The system is not observable. Okay. And you should remember, only this is acceptable only for the systems represented in parallel form with no repeated loops, poles, eigenvalues. So observability via observability map. Same, I told you, it is related with output of the system. So let us form an observability matrix with the help of these two matrices now, and its format is given here. Finally, identify its rank. If it is rank is equal to number of state variables, then it is observable. Otherwise, not observable. Or you can say, if the determinant is not zero, observable. If the determinant is zero, not observable. Simple topic, compulsory question topic, controllability, observability. Refer any text. So this is the problem. So this is the problem going to obtain observability matrix. Rank is 3, determinant is non-zero, so it is observable. It should not be any very small topic. So we can close the class today. Controllability and observability, methods to find controllability and observability. And you do one thing, you find are there any other methods to find out controllability or observability. What I have given you, controllability by inspection and controllability via controllability method. You please refer any textbook and find out if there any other method available. If any method is available, you solve these problems in that method. This is important. From the input end, from the output end, we can access the state variables. So we will continue in the next class. Thank you.